session. So we've talked about doing the reduction, like dimensionality reduction from this maybe high dimensional feature to a latent feature. And in this setting, it's like, we still have the same condition where we want to make sure that whatever we have here as the latent, we're able to reconstruct back our original data. And actually, all these conditions are in the orthogonality constraint of our previous, as we've seen previously in the previous lecture. The thing is, actually we can use that property and recast the problem again by focusing on, how to reconstruct back this Z to X by using this omega matrix. And you can think of this omega matrix as like, it is like a pseudo inverse of this phi matrix. You can think of it in that way. It's not like a total inverse, but it's something that, whatever you would, okay, I should put it this way. It is a matrix that you will learn from solving this alternative view of PCA. And it has to be the matrix that provides the correct projection back. So you can imagine that if this phi matrix is like, how should I say, it's like n times n matrix, or on the other words, you didn't do any reduction, you have the phi rows equal to the number of feature, and you make the projection that give the same size of feature. That means that your omega matrix will also will eventually be like a a proper inversion of that phi matrix. But if the size is not n times n, then you have to do the pseudo inverse. Okay. Anyway, so in this alternative view, we will be focusing on how to ensure that, how to make sure that whatever we get from this optimization problem, that is, in this case, we'll be finding the omega matrix that will ensure that whatever you have in Z here will be able to project back to X. So that means you will minimize the error between X and the projection of the Zj and omega. And in here, another thing that you have to notice about is the fact that previously our primal problem will be involving with finding only phi, like just the phi matrix. But in here, you have to find both the omega matrix and the Z vector. But you can think of this Z vector as a vector that is resulting from an off-shelf matrix projection. For example, you can pre-install Zj from phi xj, and this phi could be like a well-known matrix projection such as the Fourier matrix or the wavelet transformation matrix. So you can kind of like use some off-the-shelf matrix to do the projection. And once you have this projection, all you need to do is you could just find just the omega matrix. But if you also optimize for the Z vector, that means inherently you also optimize for this phi matrix as well, because this term can be decomposed as this. So it will be something along the line of like that as well. So by writing this Zj is like inherently writing this terms together. There's another thing about this, that is, if xj is in Rn, and we say that our projection gives set j in Rp, we say that this P components will provide the best approximation, or I should say as follows. I should say that actually this set J will be the best p-dimensional approximation, and this p principal component will be the principal component of this phi matrix. So let's say you only have like a p row, right? And usually the size of p could be somewhere between m minus 1 to n, where m minus 1 is like the size of your samples, training samples, and n is the size of your input features. And for p between these two values, the principal component should provide you the exact representation of your original data. Let me think. How should I say? Actually, this statement has one loophole. I wasn't sure if this means, actually I kind of adopt this from the book, but I wasn't sure if m is much larger than n. That could be something, because when they wrote it like this, yeah, I'm not sure about this one, because if m is larger than n, it simply means that when p equal to n, then that means that it could provide the exact representation. But if n is much, okay, I think the assumption behind this statement is that m is much larger than n. Sorry. Because if n is larger than m, then you will not be able to get the unique representation right from the beginning, because that means you have less observation than your unknown. So only this case. Yeah. Okay. Then, actually, from this equation, I have copied it here because I would like to make some comparison. Actually, with this setting, people start to think about, if we have this setting and our x is going to look like this. Okay, let me crop it a little bit. I copied the x from the previous pages. Yep. Our x should look like that, right? Thing is, if we can really learn for the good omega matrix and set J, if we really have this good solution, that means we can recover xj even though some of the xj may be missing. So it is like you can compute this entire X matrix by using these two pairs. So that was like the original idea of using this PCA for solving for a missing value. However, you cannot, this will work if you are, however, this should, it should work if you have some missing value, but there are conditions into how the missingness should happen. One of the conditions for using PCA for solving for this missing value is the fact that you have to make sure that the missing value have to be missed at random. I'm not sure if yes. Yeah, I put it here. So it will work if your missingness is at random, not structured. Because your PCA is like, once you project it down to a latent dimension, this latent dimension contains some information from your original dimension, but it is like it's your projection result. But if your data is structured somewhere, the distribution of the projection will not be maybe not unique or something.